We will continue in the product rule of differential calculus. Why calculus? How calculus? Why calculus and how calculus? So that is in discussion. So why we need calculus and then how we proceed in calculus. So that is the concept. Why we need calculus? Because we need collection. If I have rate of collection, from rate of collection, how I can get the collection? So that is the place we need integral calculus. To calculate the rate of collection to collection, then we saw that rate of collection, if I represent rate of collection, if I denote rate of collection as an algebraic equation, and for that algebraic equation, if I draw a graph, then I have independent and dependent component. The function over independent component is the vertical, and whereas independent component is horizontal. X-axis is independent component and function over x is the dependent component, that is fx or y. So if I need to calculate if y-axis is rate of collection, if I need the net collection, then I have to calculate the area. That area is integral calculus. Many times we have talked about it. So integral calculus. So for polynomial, we saw that if it is x to the power n, if the equation of the algebraic equation over independent component x, if it is x to the power n, then its integration is x to the power n plus its integration is x to the power n plus, okay. So its integration is x to the power n plus 1 divided by n plus 1. So if I have a graph and it is x to the power n with the independent component x, that is x-axis, then area underneath is x to the power n plus 1 divided by n plus 1. Okay. So this area concept transformed into integral calculus. Then we found that integration of sin x means area under sin x is cos x. Area under cos x is minus sin x. Area under sin x is minus cos x, and area under cos x is sin x. Area under tan x, accordingly we can find out. I don't know. I believe sec square x or something like that. Then e to the power x, ln x, like that. How we can proceed in the integral calculus? How, if I have algebraic equation, how we can proceed to find its integration? There are three ways. One way we discussed that immediately I can draw the graph of the algebraic equation and try to find its area. That is one. Second thing is, whatever algebraic equation fx I have, we can break it into smaller part and then we can try if I know that integration. If I know, I can achieve it. Third way is, if fx is a function for which integration is gx, then do I know any function gx for which differentiation is back to fx? If any function gx for which differentiation is back to fx, means fx integration is gx. Three ways we can find the integration. So one way to proceed is area, another way is to break it down lower side and see lower integration we know. Third is the differential way or anti-integral way. Okay, so in second way, while breaking it down, what is the integration of sine square x? That question comes. What is the integration of sine square x? What is the integration of sine square x cos x? Sine square x multiplied by cos x. What is integration of cos square x? I don't know. Integration of cos square x means integration of cos x into cos x. So here we have two functions, cos x and cos x. Multiplication of two functions, what is integration? I don't know. So this is called product rule in integration or integration by part. What is integration by part? This is the way we proceed. How calculus? Why calculus? We know how calculus. How calculus means how I can calculate the integration of an algebraic equation if I don't go through the area. One is area. If I don't go through the area, how calculus means area also. If I don't go through the area, then how I can calculate the integration of a function when we can do other way, like breaking it down. Like if it is sin square x, then sin x into sin x. If I break in this fashion, then I have two functions. Okay, consider two functions is gx and hx. What is integration of gx into hx? If I don't know, let's try to differentiation way. That is also one way. So what is differentiation of gx into hx? We found out that integration of gx into hx is gx dhx by dx plus hx dgx by dx, or gx h gx gradient of h plus h gradient of g. So that is the through area way we found out, and through our way. So our way we will discuss, and then we will discuss one type. Our way we will discuss in every way. Okay, it is the, I believe that it is the most precious one as far as multivariable is concerned. That is also the Taylor approximation of any multivariable polynomial function in the first order. Okay, so what is the Taylor expansion of any function fxy? If there is function fxy, function is any rubbish, I'm not saying rubbish thing, anything, polynomial, sinusoidal, and then exponential, logarithmic, Fibonacci series, and so many mathematical expression, that is fxy. If I have fxy and I need to find out the derivative of hx into gx, gx into hx. What is derivative? If I have a function over independent component x comma y, or if I have a function over independent component xy plane, then what is polynomial approximation of this function as far as Taylor series is concerned when we have order of 1 only? Then that is the fxy equal to whatever we have, we can again say fxy equal to dfxy by dx into x plus dfxy by dy plus y. If I go beyond the first order, then we have d2fxy by dx square, I believe by factorial of 2, plus 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 dfxy by dx into dfxy by dy plus d2fxy. I believe it is complex. It is more than this. Okay, we have talked about it, we have proved many ways. Leave it. So what is the Taylor polynomial approximation of any function fxy in single order? So that approximation is dfxy by dx, fxy equal to dfxy by dx into x plus dfxy by dy into y. If I say fxy is z, that is the height. If I have xy plane and I have xy so many points on the xy plane, if I draw a function over xy plane, I'll get the altitudes, z axis. Any point on, if this is xy plane, if I take any point on xy plane, for that xy plane, if I go with function over x comma y, function would resultant in a scalar value, that is vertical. If I connect all these vertical points, I get a surface, that is 3D. So if I have fxy, then fxy equal to dfxy by dx, partial derivative along x-axis, into x plus dfxy by dy into y. This is Taylor series first order. If that is the case, consider fxy is z, then z equal to dz by dx into x plus dz by dy into y. If that is the case, then delta z gradient, delta z equal to dz by dx into delta x plus dz by dy into delta y. Okay, that is the scenario. Now consider that z equal to, or fxy is a function over x comma y. This function is x into y. This function is x into y, or this function is gx into hx. Gx equal to x and hx equal to y. Possible, right? So if I have kind of a fxy function over x and y, consider function over x and y equal to x into y. Function over x and y equal to anything can be there. X into y. So now we are calculating delta z equal to dz by dx into delta x plus dz by dy into delta y. So now delta z is nothing but derivative of x into y. Derivative of x into y. Consider x is ux. ux is a function which is x and y is a function called u vx. ux vx. V for victory. So now we are trying to calculate derivative of delta z is nothing but delta derivative of u into v. U is a function, v is a function. Okay, or gx, gx or hx, whatever it is. I consider fxy equal to x into y. If I consider x as gx and y as hx, then delta z equal to dz by dx into delta x plus dz by dy into delta y. Now delta z, that is derivative of gx into hx. This is what we want. Derivative of gx into hx equal to dz by dx. Z is gx into hx and x is gx. Delta x is derivative of gx plus dz by dy, dgx into hx by d of hx into delta y, d of h, derivative of hx. If I simplify this, dgx into hx divided by dgx, it is as good as calculating the gradient partial derivative with gx. If function is gx into hx, dgx into hx by dgx means partial derivative with gx. If that is the case, it will result in hx. If I have a function xy, if I do partial derivative with x, it will result in y. So dgx into hx by dgx will result into hx. So hx into dgx plus dgx into hx by dhx would result in gx into gx into dhx. So d of the gradient of hx into gx equal to hx gradient of gx plus gx gradient of hx. This is product rule in differentiation through Taylor series. If I go through algebra, then if I have a line, if I go through algebra, if I have a line, what is equation of the line? In 2D, if I have x-axis, y-axis, there is a line, then what is the equation of the line? Equation of the line, that is y equal to what? Fx equal to what? Then y equal to dy by dx into x. What is the slope of this line? If there is 1 unit of change along x-axis, how many unit of change we see along y-axis? That is slope of the line. Slope of the line into any x. Keep changing the x, you will get the y. That is y equal to dy by dx into x. This is single, this is 2D. If I go for 3D and if I have, okay, so we have demonstrated it. If I have xy plane and there is a surface that is kept on xy plane. So if this is y-axis and this is x-axis and this is y-axis, if I keep y-axis constant and move it like this, then at any point x comma y, how much z I see that is formed. Earlier z is 0. How much z we can see, that is dz by dx into whatever x is. Okay, now keep the x constant and then move the y, or keep the x constant and keep the x constant and move the y. How much z it has got it? Okay, when there is no movement along x-axis, only y-axis is going up. Then at any point x, it is dz by dy into y. Okay, let's do both things. If I keep this constant and move it up, then z moved is dz by dx into x. Then keeping x constant and then I move it up, then again z is up. Then what extra z got is dz by dy into y. Or if I keep x constant and move y, then it is dz by dy into y. And then keep y constant and move x, then again extra movement has come, that is dz by dx into x. So net z, what we see is z equal to dz by dx into x plus dz by dy into y. This is pure algebra. Pure algebra. Okay. So through pure algebra, we came to same equation. Through first order derivative of the Taylor series, we came to same equation, that is dz by dx into x plus dz by dy into y. Okay, so we proved that the derivative of u into v is nothing but u derivative of v plus v derivative of u. This is called product rule in differentiation. Mind blowing. Mind blowing. It opens a path. It opens a path to infinite. What is derivative of sin x? Anyone would say cos x immediately. What is derivative of sine square x? I don't know. Oh, sine square x, then I have to calculate this way, that way. What is derivative of sine 2x? Okay, someone can go with the chain rule. Sine 2x, derivative of sine 2x is nothing but cos 2x and then with 2x, 2 cos 2x. 2 cos 2x would be derivative of sine x. What is the formula of sine 2x? Sine 2x. Sine x cos x, I believe so. I don't remember much. Sine x cos x plus again sine x cos x plus cos x sine x. That is 2 sine x cos x. Okay, if I go with for derivative of this, what is derivative of sine x into cos x? No one knows. So to proceed further, how calculus? To proceed further, then we need product rule. What is the differentiation of sine x into cos x? So sine x and derivative of cos x, that is minus sine x. So minus sine square x plus cos x and derivative of sine x. Then it becomes cos x cos x. So minus sine square x plus cos square x, that is cos 2x. So derivative of sine x into cos x, derivative of sine x into cos x, I believe it is cos 2x, because sine x and then derivative of cos x is minus sine x, so minus sine square x. And then cos x, derivative of sine x is cos x, then cos square x minus sine square x. Then it will come to cos 2x, plus cos 2x or minus cos 2x, whatever it is. So this is product rule. So this way we can proceed further in integral calculus. But right now we are in differentiation only. What is other proof of the product rule? Consider I have to find differentiation of u into v, where u is a function over x and v is a function over x. Ux into vx. We can say ux is x and vx is something else, x again or y, whatever it is. Ux into vx, u into v. What is differentiation of u into v? Consider a formula, algebraic formula, that is u plus v whole square. U plus v whole square. What is u plus v whole square? That what is the different? What is u plus v whole square? As per algebra, it is u square plus v square plus 2 uv. What is differentiation of u plus v whole square? Okay, what is differentiation of u plus v whole square. Differentiation of u plus v whole square. Differentiation of u plus v whole square is nothing but 2 u plus v and then differentiation of u plus v as per the chain rule. U plus v whole square, differentiation of x square is 2x as per the polynomial. Differentiation of u plus v whole square is 2u plus v and then differentiation of u plus v. That will result in du plus dv, gradient of u plus gradient of v. 2 in bracket u plus v and then in bracket gradient of u plus gradient of v. That is gradient of u plus v whole square. Let's break the u plus v whole square. Then it becomes u square plus v square plus 2uv. Now gradient of u square is 2u gradient of u plus 2v gradient of v plus 2 into gradient of u into v. This is what we want. Gradient of u into v. So whole is 2u gradient of u plus 2v gradient of v plus 2 gradient of u into v equal to 2 and then u plus v bracket close again multiplied by bracket open gradient of u plus gradient of v. Everywhere 2 is there, 2 I can take it out. Now it is u into gradient of u plus v into gradient of v plus gradient of u into v. This is what we want. Equal to, if I solve it other side, then it becomes u into gradient of u plus u into gradient of v plus v into gradient of u plus v into gradient of v. U into gradient of u, v into gradient of v. They are both sides. Cut down. So gradient of u into v equal to u into gradient of v plus v into gradient of u. Proved, right? So product rule we can prove through this is what I say. When you go for the integral, any calculus, break it into a smaller part and see if you know the gradient. If you don't know, again break into smaller part and see if you know the gradient or integral, whatever. Then you can tackle it. So I know the gradient of polynomial, that is, if it is x to the power n, the gradient is n x to the power n minus 1, where integration of x to, whereas the integration that is x to the power n is n x to the power n plus x to the power 1, integration is x to the power n plus 1 divided by n plus 1, whereas derivative of x to the power n is n x to the power n minus 1. This is what we use. U plus v whole square, gradient is 2 u plus v and then gradient of u plus v. Break this side and that side, complete it, and you get gradient of u into v equal to u gradient of v plus v gradient of u. Very important. The multiplication gradient is very important. So we will proceed. One more is, that is logarithmic. Okay, it is high density gradient. So better we will see it in next session. How we can go with logarithmic. There is one called logarithmic and we'll complete it. So idea is that we have one proof from our side, that is Taylor's one, and Taylor, and then in kind of algebraic equation through also we got that z fxy equal to dfxy by dx into x plus dfxy by dy into y. This is proved one. Or z equal to dz by dx into x plus dz by dy into y. Then delta z equal to dz by dx into delta x gradient plus dz by dy into delta y. Okay, this is our proof, that we prove the product rule. We prove the product rule in the calculus for the gradient. Slowly we will move to the product rule in integration through the gradient only. So that we will see.